In this video, we're going to look at a particular type of experimental situation where you perform a reaction and collect a gas over water. And essentially what this collecting gas over water type of experiment entails is you're capturing a gas into a container and displacing water that was originally in that container. And the gas, one thing that it cannot do is react with the water. It has to just displace that water. And it turns out that this is kind of how it works. So if you look at this particular setup that I have here, this setup suggests that you have an Erlenmeyer flask that is completely filled with water and turned upside down, and the top of that Erlenmeyer flask is now placed underneath the top of the level of an open container also full of water. And there is a hose, an open-ended hose, that's piping into the opening of that Erlenmeyer underneath the level of the water, that's then connected to a container over here, and I have a test tube drawn here, that's going to have a reaction that produces a gas. So let's say a reaction happens and bubbles start to get produced. What will happen is these gases are going to travel up through that hose and all the way down the hose and up into the opening of that Erlenmeyer. Well, what's going to happen to the level of the water? What's going to happen is the water level is going to go down. Why? Because the gas bubbles are being collected into the Erlenmeyer, and the water level here is going to increase. Now, the amount of volume that is collected or displaced of water here, the water volume displaced, should also be equal to the volume of gas generated. But I will say one thing about the pressure that is actually being exerted inside this area within that Erlenmeyer is actually going to be equivalent to the pressure of the atmospheric pressure pushing down on the top of the water in this container. So essentially, what's going to happen is the pressure pushing down on the outside, right here, and the pressure outside should be equivalent to the pressure on the inside of that container. Now, the outside obviously is going to be equivalent to the atmospheric pressure. The way we write that is pressure sub ATM, ATM meaning atmospheric pressure. Sometimes you might hear this called the barometric pressure. But the inside is a very interesting concept. It turns out that you're going to go, oh, well, it's just the pressure of the gas that's inside that was generated in this reaction that happened in the test tube. Well, that's not 100% true. Because you have water inside that particular closed container, if you will, it turns out that water has this level of volatility that generates some level of water vapor being also in that inside of that Erlenmeyer. So the inside pressure is actually, according to Dalton's partial pressures, is the sum of the pressure of the gas and the sum of the pressure of the water vapor at a particular temperature. And the level of the water vapor pressure is dependent on that temperature. So what we can say, if the pressure on the outside and the pressure on the inside are equivalent to one another, and this is the pressure on the outside, this is the pressure on the inside, then we can set them as equal to one another. So eventually what we're going to want to do is calculate what is the pressure of the gas alone that's generated in the reaction. And in order to do that, the pressure of the gas would be equal to the pressure of the atmosphere minus the pressure of the water vapor at that particular respective temperature that the experiment had been run. So these values of that water vapor pressure that is dependent on temperature can be found in a table in your textbook in table 9.2, and it has multiple values of water vapor pressure. I will say that more often than not, these water vapor pressures are given in torr because the water vapor pressure is fairly low. But if you'll notice, the higher and higher that temperature gets, the more and more increase you have in water vapor pressure. And in fact, you expect at 100 degrees Celsius the water vapor pressure to be 760 torr, which is 1 atmosphere. And that's the value at which our water will change phases from liquid to gas. So you would need this table as a reference anytime you're doing a problem where you're collecting gas over water. So how about we try one of these problems? Okay, so it says a sample of oxygen gas is collected over water. So anytime a collection over water problem is done, they will say that. You're going to see this phrase in the equation, and so that you know that you need to be using this particular equation here to help you solve anything else that they're asking about that particular gas. So keep this in mind. This and this go hand in hand. So it says you have a sample of oxygen gas that is collected over water at a temperature of 29.0 degrees C and a pressure of 760 torr. The 760 torr is going to be the pressure at the atmosphere. So that's the value that it's referring to. With a volume of 0.560 liters. Now the question asks, what volume would the dry oxygen, this phrase right here is pretty important, have at standard temperature pressure or STP? So first off, let's kind of think about this just a little bit. What kind of equations am I going to need? Well, one, you're going to need this equation because of the collected gas over water statement. And then if you look at it, you know that you've been given temperature 29.0 degrees C. You've been given an atmospheric pressure 764 torr. You've been given a volume 0.560 liters. And then the question actually asks what volume. So it's asking for a new volume. Would the dry oxygen have at standard temperature pressure? So it's literally saying at this temperature, standard temperature, and this pressure. Standard pressure would be 760 torr or 1 atm. So to me, this looks like a combined gas law problem. So what I'm going to do is I need to kind of figure out what do they mean by this word dry oxygen. Well, dry oxygen is the oxygen without water vapor in it. So what is that going to be? That's going to be any volume of the oxygen of that gas just solely associated to the pressure of that gas, not including water vapor pressure. And so what you would do is instead of using atmospheric pressure here, you need to use dry oxygen pressure. So that's not the true pressure. We need to use this of the oxygen gas. So this guy right here. And so how do you solve for that again? The pressure of a gas, in our case is O2, is equal to the pressure of the atmosphere minus the pressure of water vapor. And so let's solve for that really quickly. And we know our atmospheric pressure is 764 torr, and we need to subtract the water vapor pressure, but that's completely dependent on the temperature. So let's go back to our table, and 29 degrees Celsius gives us 30.0 torr. So we're going to subtract 30.0 torr here. And when we subtract 30.0 torr, we're going to get a value of 734 torr for the oxygen. And this would be what we call dry oxygen. So that's the value we're going to use. So let's write our combined gas law again, PV over NT on one condition and PV over NT of our second condition. And nowhere in here have we said anything about the amount of moles, so we can't use the N in this problem. But we're going to solve for, let's say this is the experimental condition on the left-hand side, and this is the STP condition on the right-hand side. And so we'll plug our values into this equation and solve for what we don't have, which is our volume here. So our first pressure 1, is going to be the pressure of our gas. That's 734 torr times the volume of 0.560 liters divided by the temperature, and this is 29 degrees C, but we're going to add 273 to that and give us a Kelvin value of 302 Kelvin. So make sure that you're using Kelvin for temperatures. This will give us 302 Kelvin equals pressure 2. This is going to be standard pressure, so 760 torr. And the volume, we don't know. This is volume 2. And then the second temperature, standard temperature, is 273 Kelvin. And so to calculate this value, what we're going to do is we're going to multiply by the reciprocal of what's in this fraction. So this is 273 Kelvin divided by 760 torr. 273 Kelvin divided by 760 torr on both sides. Cancels out on the right, leaves us with just our volume. And then when we take our 273 times 734 times 0.560 times, divided by 760 torr divided by 302 Kelvin, this gives us a value of 0.4, and we're going to make this 3 sig figs, 0.489 liters. Okay, and so this will be our volume of our dry oxygen at standard temperature and pressure. And really, this is just a classic combined gas law problem. The only thing different about a collecting gas over water problem is you're generating the pressure of a dry gas. And so you're going to have to do what I call correcting the pressure using water vapor's pressure and subtracting that from the barometric pressure. And then using that result as your original pressure of that dry value, or dry gas. In our case, that was oxygen. So this is how you do a collecting gas over water problem using the combined gas law along with the idea behind water vapor pressure.